Science is the most modern tool we have, most modern tool consciousness has, to try to tell an accurate story about what reality is. As that story has changed over time, as humans have gone from thinking the world was a certain thing to thinking another thing and so on, the thing that's changed is how we feel in our existence, the thing we're paying attention to, what we're focused on, what we have access to, and what we can do, right? We're currently in a level of understanding that allows us to access electrons. Pretty much that's it. And we can't even fully access electrons, right? We don't understand electrons to the point where we can tell you why it has any of the properties it has. Quantum mechanics doesn't tell you how to think about the world, right? General relativity doesn't give you a full picture. It doesn't tell you anything about the quantum mechanical stuff. So what picture of the world are you supposed to be carrying? What is the main mystery? Why are the data points the data points?
Where do they come from and why are they there?
Yeah.
The purpose or the meaning, underlying purpose for why things even exist.
Yeah. And why does this matter? You know, why does that all matter? Why does the answer matter? The answer we don't have.
Because it allows us to live in a perspective or to live with a perspective that is more
With
accurate.
that answer, we should be able to occupy a perspective that sees, that knows those effects, and therefore can do what? All the things on purpose. We can start building machines to on purpose do the things that nature can do. This will change things in a dramatic way. You can use anything with mass to alter it into any other legal form of mass, up to the same amount of mass that you started with. Different arrangement, right? And there's only certain legal forms. The ones that obey the transforms of the periodic table of elements. All the atoms that make up possible structures. If you found the true laws of nature that allowed you to frame the real structure of reality so that you had an actual picture of why all the properties that are in reality, the things it's impregnated with, just its essence, the things we characterize when we write down things like the speed of light or the Planck's constant or the gravitational constant, these things that were really hard to discover because you don't see them when you first look out because you're looking out through your very blind perspective, the one that doesn't tell you anything about even electrons.
Like E equals mc squared. How does that apply to my life?
E equals mc squared means that energy, which you already know why matters to you. Energy I need for my battery, energy I need for all the stuff that I now use, so I care about energy. But it's equal to mass.
To think.
To think. You need food, yes. Even food is energy. Exactly. Your whole existence revolves around gaining energy. And if you understood what energy was, you could gain it easier. Mm-hmm. Right? Right now, energy is one of the big mysteries of reality. It's made up of mass times by the speed of light squared. The thing you care about, energy, can be got from mass. And c squared, well, c is 2.99792,458 times 10 to the 8 meters per second. It's a big number, 10 to the 8, right? It's a really big number. Square it, now it's a really big number. So mass gets converted by something that's huge into energy. So mass is extremely compactified energy. Now think about what this really means. If you understood the framework of reality, if you had a picture in your consciousness that projected for your sight what reality was based on the true story, the one that automatically included the effects that we actually measure in reality, right? The stories we have right now may be the best we can do, but nobody's come up with one whose parameters, whose assumptions lead us to any of the actual properties we're trying to explain, right? We've got measured properties that need to be explained. These are the magical effects, the characteristics reality has been found to have. And if we ever get a picture that makes sense of them, it means we are gaining the ability to start making machines that use those effects on purpose. The true alchemy effort, literally.
So like the building blocks of reality.
Yes, Understanding the building blocks of reality will allow you to understand the transforms between those building blocks.
And then we can build reality.
Yeah, on purpose, all you want.
With intention.
With the correct understanding of reality, the dirt underneath your feet becomes as valuable as anything you've ever imagined. We've been making up stories, since, I guess, before we were even humans, right? Cats make up fantastic stories about the world that allow them to accurately hunt, right? And we've been making up stories at least that accurately, allow us to effectively get through the world for a long time. But it's only been recently in history, since the birth of science, that we've been doing this in a very, very specific way on purpose. Meaning, there was the first human came along and decided to take the question of reality seriously enough to measure. Think of this. Up until that point, at some point, whether we got the right guy or not, Galileo, Alexander, I think, or his teacher, okay? Or at least in history that's what's recorded. But still around that time, apparently before then, no human who saw the world a certain way had thought to come up with a way to objectively find out if what their eyes told them was true. Think of that. Not until recently did the first human ever do that. That was the birth of science, to start using measures to make sense of what you're seeing, okay? Now, measurements are still the most reliable things we have for truth, right? These are the things you can actually objectively get from an environment.
So not just correlation and speculation.
Yeah, and the goal has been to make sense of the stuff we're seeing. So since we started employing the methodology of Alexander and all the paths since then, all the great scientists since then, who came up with more ways to look into the world more specifically, to start measuring things that we were claiming about the world and actually seeing what the real property was. We've landed in a position now where we have this list of constants of nature. In fact, here they are. Let's go to code at it. Here's a website. Here's one of the constants of nature, electron magnetic moment to nuclear magneton ratio. That's its name. I'm going to show you the list. This is the best we got, people. It's funny to me because these are the most important parameters, and this is the most official site for these most important parameters in the world. And look, it's very, very, very just computer script. This is it. Names, values, uncertainty on the value, so you know how well we know this number, okay, which is a fantastic thing. It's not just a claim, it tells you how well we know the claim.
Like how predictable
Great.
it is.
How accurate it is, and we've been trying to get it more and more accurate. This is as of this most recent update, how the most accurate constants of nature measurements and the units that they're in. Okay, there's this long list of measured properties built into the world, the constants of nature. Okay, nobody knows why. These are the actual facts of reality, and nobody knows why. Okay, nobody's allowed to directly look in our modern society because you can't get paid to do this, which is formally a way to make us so we're not allowed, right? Why? But I want to make it really clear why. What happens when someone figures out these? What happens when someone knows why the world is broken into a way that has these properties very specifically?
It takes away the power of those.
The power structure that we are
hierarchy
shackled by right now completely dissolves. It's not a revolution in war. It's a revolution in technological insight, where you gain the ability in situ, in place, as long as you have access to mass, or say nitrogen air. Then you let some nitrogen air into your machine, you make the machine twist it into what you exactly wanted, right? You get the output you wanted. You didn't need to rely on a system of transportation, on a system of permission, on a system of exchange, on a system of protection. You didn't need any of that for your thing. This level of understanding should transcend all of those limitations because you can't take away their access to mass.
Does it essentially turn us into gods?
Maybe in comparison to the shackles we're under now. When you have access to any resource for free, when you're a kid at 12, when I was a kid at 12, you know what I would have done? I'd have started making my own radios out of the best materials, not the cheapest materials. I'd have started theorizing the best possible way improve on some effect that I was trying to get. I started making my own computers. I would have not been limited by the thing, I can't afford that. My curiosity was rich enough to take me to try everything by then if money wasn't the problem, right? I've been trying to find a story that you could put together, that the data points put together, that you could then, okay, that's why I get all the data points.
Yeah.
Does that make sense?
I think, yes. What I remember...
Reverse engineering is what we call it, right?
Basically, starting, if I were God, how would I go about creating this universe?
Yeah.
Essentially.
Yeah. I want a complete deterministic containment of the actual essence of reality. Right now I have a list of numbers that means nothing. You could memorize all the numbers and hold them in your head, and still you wouldn't have a picture that contained those properties in its structure in any way. You're just memorizing a list. I'm not just here to report the effort. I actually have fantastic news of where we got. We actually have found a story that goes all the way from the beginning out. And let me see if I can tell it. If we imagine starting without a universe, okay? Let's say exactly what we mean. There's an infinite void. There's no stuff in it. There's random waves going everywhere. There's nothing that repeats. There's nothing that persists. If you and I were gods looking at this infinite void, but somehow not in it, because then we would have stuff in that void, right? If that were a thing we could say coherently, and we were looking at it, you could point to anything in there to try to tell me, look at the character here, and then if I looked, I would not find it, okay? So anything that does happen there never happens again. That's what I mean by infinite void of nothingness, okay? Nothing is repeatable, nothing is measurable, nothing can be made sense of. By definition.
Chaos.
It's chaos and endless. Okay, I want to ask, what does it take to go from that nothingness to something, to have something that persists? Anything, the minimal possible thing. What's the smallest step from this nothing, chaos, infiniteness to a universe of structured order? It turns out mathematicians have already found the answer to this.
Okay.
I was, trained classically through physics, and we were not trained anything, at least not through my training, anything about knot theory, okay? But it turns out that there are a whole class of knots. There's the simplest one all the way to more and more infinite complexity, combining more and more features of the knots, right? But the simplest possible knot is called the hyperbolic figure 8 knot, okay? And it's the simplest possible hyperbolic knot. There's one simpler one that's only 3 instead of 4, it's called the trefoil knot, but it's not hyperbolic. What's cool about hyperbolic is all hyperbolic knots admit rigid structures. If you formed a hyperbolic knot, then the complement of that knot being formed, the wave motion of everything else in reaction to the formation of the knot, emits a rigid structure, a grid.
A parameter.
A grid that repeats the whole thing over and over and over, okay? Each knot gives you a different rigid structure, but each knot emits a rigid structure if it's hyperbolic, okay? There's the simplest possible manifold.
So yeah, what does hyperbolic mean? What you just said, is that the definition of hyperbolic?
Great question. What does hyperbolic mean? I'm going to try to answer that like 5 ways, okay? First of all, the classic hyperbolic structure in mathematics is shown like this, with this conic center to it, the cone on cone, right? This is back there.
Yeah, like a torus almost.
Yeah, well, it's a cone that goes through the center, and there's an inverse cone out there. Yep. And we mean it keeps going. We're just looking at a portion of it, okay? But why is this called hyperbolic? What does it have to do with hyperbolic at all? Well, it's the exact same cone that we talk about when we're talking about the light cone in four-dimensional space-time. Any point, the speed of light restricts where you have access to. It basically divides the world in half. Half of the world is now accessible to you, and half of it is inaccessible to you forever. Because of the speed of light, okay? But it does this exact division. It makes this half inaccessible and this half accessible, okay? All right. Hyperbolic also means that we've got circles, right? If I slice this cone this way, but exactly this way, perpendicular to the plane of it, right? Then it'll be a circle. My slice cuts a circle. Okay, if I do it higher, it's just a bigger circle. It keeps going, bigger, bigger, bigger. All circles are captured by this cone, right? And we have an inversion, and then all circles captured by the cone. But also, if you slice this way, I'm still perpendicular to the board, but I tilted it, okay? So I'm not flat this way anymore. And now we got a ellipse, right? We have it cuts like that, and we form an ellipse. We have all ellipses until we end up with a hyperbola, or parabola. So we get parabolas, we get hyperbolas, we get circles, we get cones, all built from the same structure. They're just different parts of the same structure that are all balanced together. You can't remove any of those from the system, okay? All right. That's part of what we mean when we mean hyperbolic. Another thing we mean is algebraically. The same properties here, this is a graph of these same sets of properties. If we do x squared plus y squared plus z squared equals 1, let's do it on Wolfram alpha. Okay, x squared plus y squared plus z squared equals 1. We get the unit sphere. Okay, this is the equation for the unit sphere. Note it has 3 parameters, x, y, and z. It's 3-dimensional. Okay? Now, what we're doing when we're talking about hyperbolic space is we're talking about this. This is part of hyperbolic space. This is spherical.
It's 3-dimensional.
3-dimensional. But we're also talking about x squared plus y squared minus z squared equals 1. Let's try that. I'm just going to change that plus to a minus. Oh, the one-sheeted hyperboloid. That's around this one, like that. Okay? Part of the same structure. I didn't draw it until now, but there it is. And now, let's add that one to our list. We also want to do x squared plus y squared minus z squared again equals 0. These are all hyperbolic surfaces here. The cone, that's the one I started with, okay? And then we'll add the last one, minus 1. And we get the 2-sheeted hyperboloid. That one. Okay, so this is x squared plus y squared minus z squared equals minus 1. These 4 different sheets, different surfaces, different relationships that are boundaries are all what we mean when we say we have a hyperbolic structure. Okay. These are the unit surfaces of hyperbolic space.
But every hyperbolic, any hyperbolic figure is going to have...
Yes, all of that structure in it.
All that structure, okay.
Yep. Okay, well, when we talk about a structured surface or a manifold, the simplest possible manifold has a symbol called GGI. This is the Giesking constant. And if you multiply it by 2, you get the hyperbolic figure 8 knots volume. The volume complement of the hyperbolic figure 8 knot, okay? It's a certain number. It's exactly equal to twice the Giesking constant. So this is the simplest free manifold there is, and you double cover it. So you use the simplest thing that you can twist together to be its own root, to make the boundary that closes itself, the wall that it pushes against, right? You just use it twice, and you get the hyperbolic figure 8 knot. Now, I'm saying then that the simplest possible structure you can make that is structured, that will persist with its own structure, is this one. It's the root of the simplest possible universe. If you try to imagine starting from a random void to begin with, and you want to intentionally put together waves, the simplest construction of waves they put together to make a closed perpetual system would be this set, okay? All right, well, this equation, or this set we can look into, it turns out. So this is actually equal to I. We define I. I'm sure you've been introduced to I, but it's called the square root of -1, right? And this we visualize graphically on the xy plane, xi plane. We can have 1 here, and maybe put the unit circle in there. If this is 1 for x, then this is I in the other direction. So it's just a different direction, another dimension with a value or magnitude of 1, right? Its radius is the same as 1, but it's a completely different direction from 1. So the square root of -1. -1 is a flip halfway around the circle, right? It's this point right here. It takes you halfway around the circle, -1. Square root of -1 means half of that flip. This power half here means literally just halfway. So you end up just right there. Okay. Now, there's another number since we're here. Let's put, this one's called the imaginary golden ratio. Beautiful name. It deserves that name, by the way. A lot of names people try to give because they're trying to market. This one deserves its name. It's directly related in many beautiful ways to the imaginary unit, I, and to the golden ratio. But we'll get into some of that later if you want to. This one's equal to -1 to the 1/3. Almost the same. It's like a brother to this one, right? It just goes 1/3 of a flip. If this is half of a flip, then 1/3 of a flip is something like right here. So imaginary golden ratio is right there. Okay, obviously it still has the same magnitude, 1. Its radius is 1, its position's different on the circle. Okay, we're using that in, and I know you probably don't know what a dialogarithm is. That's okay, we're going to explain it. Minus a dialogarithm of the imaginary golden ratio. A dialogarithm, or it's also got the name polylogarithm of order 2, which means a two-dimensional logarithm. You've probably used log in the calculator once or twice in classes. Yeah. So logarithm's that. But if you have a system that's two-dimensional and it has a logarithmic relation this way and a logarithmic relation that way, then you can use a dialogarithm to represent it. Okay. So in here we have dialogarithms, the difference between two of them, who have different arguments. But their arguments are very related. One's the imaginary golden ratio, the other one's 1 over the imaginary golden ratio. The inverse? Opposites of each other.
Would be inverse? Or?
They're multiplicative inverses. Okay. Yeah. Beautiful start. We have a two-dimensional logarithmic structure using the most beautiful possible operators in rotations. Why? Because these are the ones that give you the grids, right? You can get a square grid or a triangle grid, right? You can tile a plane with squares or triangles. And these are the two operators that do that. Beautiful, beautiful start. Okay. Well, let's tease apart. Actually, before I go into details, let me run through a fast version of where this is going to take us. I'm saying we have a minimal root here for a structured universe, okay? And that universe, that root here, has a complement. It's like you tied a knot in the wave. The wave has to go around this closed path. But as it's going around, it drags stuff with it and ends up doing all the transformations, okay? It's creating a structure on the outside in response to that, over and over the same structure. That's why it's gold to us, because it's making something that is persistent, right? Same thing over and over, a perpetual structure. Okay, well, the outside, to find what it looks like, we just do this. Drop the I, we want the real version instead of the imaginary version. Take the dialogarithm, 1 over the imaginary golden ratio, plus the dialogarithm of the imaginary golden ratio. All I did was change the sign from minus to plus and drop the I, so it becomes the real conjugate of the hyperbolic figure 8 knot. And what is it equal to? It's equal to 4 pi squared over 288. It's actually something that brings us directly to Kepler and the most beautiful limits in hyperbolic spaces and sphere packings, but we're not going to do all those details right now. I'm just pointing out that it has this projection. This guy makes this, so these two come together. Now, this is a double covered sphere. It's a sphere that you make, a unit sphere, whose boundary is made twice.
So it's like a double layer almost.
Double layered sphere, good.
Yeah.
Okay, and that double layered sphere is divided up by 288 ways exactly. Now this is exciting because 288 is exactly the number of transformations that the tetrahedron that we're talking about, structure that this is based on, can undergo and still look the same. So this hyperbolic figure eight knot has this many possible ways of being twisted into something else. Okay, and 288 happens to be the exact number of constants in nature. Okay, now what's the picture? We've formed the hyperbolic figure eight knot. We've twisted up some domain. Out of this infinite void, we took some finite spot and twisted up some domain into the hyperbolic figure eight knot. Now we have this repeated structure, and its complement, the thing that it makes when we do that, is this. Some sphere that's got a double shell in there, but they're the same radius, okay?
So this is essentially a container for the chaos.
Yes, yes, okay. Good. A container for the chaos. Okay. Once it's created, the container continues containing itself. Mm-hmm. No matter what chaos is passing through it, the container continues to contain itself in that structure. All right, so let me make this smaller because there's one more layer. Inside here, there's a double layer here, right? But inside there, we have our figure eight knot that's making it, right? Or it's not really inside there. It's the whole way the thing divides is the boundary of the hyperbolic figure eight knot. But I want to represent it in your mind as existing. So let's hold it in the middle of this guy.
Okay.
Once we've created this, that's a great idea. This is kind of what we're talking about here, this shape, okay? This shape wraps around a waveform. If you followed the boundary of this, you can go all the way around forever. If you started out inside, you're trapped inside. If you started out outside, you're trapped outside. That's what I mean by this. This whole double covered sphere is also internally divided by the boundary of the hyperbolic figure eight knot. But also, since the hyperbolic figure eight knot is double covered, there's one more layer. You can surround a sphere by exactly 12 spheres. If you stack spheres around spheres, you can touch exactly 12 that are all touching the middle one.
Right.
Okay.
So that's sacred geometry.
So yes, so this picture here, we created this first three-dimensional sphere, but it's double covered, the middle one. And outside it, there's 12 other spheres touching it that are undoing exactly opposite what we did inside, so that the whole thing ends. Then now we're done. We've twisted but untwisted the system, right? We're balanced the whole system. And what are we saying now? I'm saying this is the simple, outside this is still chaos and noise. Okay? But here we have a structured system that continues to siphon all waves in the way that its structure takes them, all the way in, and continues using its structure to process all waves, in this way. All right. Follow me so far?
Yeah, I think so. So within this container, this hyperbolic container, the hyperbolic figure eight knot, it is created, let's say, it's created perpetual, persistent direction or
partitioning structure.
Flow,
exactly.
Pathway.
The waves are breaking up into certain dynamics that always go over and over and over the same thing.
Yeah. So it's almost like the riverbed that guides the water.
Yeah.
Of the direction of the water.
It's the structure of order there.
Yeah. Okay.
Great. And we're done now. The good news. So the simplest possible model of a persistent structure, I'm saying, is just this. Okay? In fact, 12 spheres around a double covered sphere. Let's talk about the 12 spheres real quick. I can do one sphere and divide it by 5 factorial. This is 5 dimensions factorized in all the possible ways they can be. Okay? I'm starting with 5 dimensions because in physics we have 5 dimensions.
We have measurements?
Of measurement. Yeah.
Mass,
we have time, space, charge, temperature, and mass. Okay? Every other kind of thing you can make a measurement of. Literally, this is a very strong thing to be aware of. If you're not aware of it, it's very important to be aware of it. Every other kind of thing you can measure is just broken down into those 5 things.
It's a combination.
It's just more combinatorial complex, but made up of those 5 things only.
Yeah.
There's only those kind of things we can measure. That's a big thing to be aware of. Reality only shows itself in 5 faces, right? 5 things can be measured of reality. Different magnitudes of those 5 things, but there's 5 things of essence that can be measured.
Essential, elemental, like Plato's.
Yeah.
Like, wasn't Plato's thing 5? The
5 platonic solids.
5 platonic solids, yeah.
Yeah, and also 5 is important to the primes. Why? It's the only double twin prime. The only double twin prime. So we're keeping 5 dimensions is important here because we have 5 dimensions of measure. Now, I didn't need to add of measure if you were a physicist because you knew I meant that. But that's what dimensions are for physicists, right? The things we can measure. And then we give numbers to the greater measures of those things, or lesser measures and so on. They are just measures of time, measures of space or length, measures of charge, temperature, and mass. Good. All right, so I'm taking our first sphere of our 12 spheres and just imagining, what if it's divided by all of the factored ways that 5 things can factor? All the ways 5 things can factor, okay? Our 5 dimensions completely divide this thing. And then let's take another one that does instead the derangements of 5 things. This is all the ways you can start with 5 things and change the arrangement of them, change the order of them, with the restriction that everybody has to move. Nobody gets to stay still during a swap. Okay? With that restriction, this goes to this. Okay? Still for 5 things, it's a rule for 5 things, but it's a rule that everything deranges. Nobody gets to hold still when you're dancing. All right? And then now I want 4 more kinds of spheres. Let's say,
kind of like musical chairs.
Yeah. Another kind of 4 more kinds of spheres. And I'm going to divide each of these spheres by, let's say this one's 35 things. I'm going to tell you why later, in a second actually. The next one by 18 things. The next one by 32 things. And the next one by 8 things. Okay, these special numbers.
So that's 6 spheres out of 12.
That's good, yes. So let's fix that. Now I'm going to say we want 1 of those, 2 of those, 3 of those, and 4 of those. Now how many do we have?
3, 6, 10, 12.
Good. 10, we have 12 total spheres. That's our outer 12 spheres we're talking about here. All of them together now, but they're divided up differently in the denominator, right? One of them gets divided by all of the factors of 5 things. The other gets divided by all the derangements of 5 things. And then, which is 44, by the way. So this one's 44, and this one's 120. Okay. Here's the cool thing. In mathematics, this is well known. This all collapses to pi to the 12 over 12 factorial. Very famous in mathematics for 2 reasons, which is why it makes it even more famous, okay? It's the exact volume of the 24-dimensional unit hypersphere with radius 1. Okay? This is the volume of the 24-dimensional hypersphere.
It's also equal to the exact density of the Leech lattice.
So this is a place in geometry where if you're talking about, let's stack spheres, and then you look at the gaps left in between, and we talk about the density of the spheres compared to the gaps. Okay, you with me? Well, if you go up in dimensions, you get some surprises. Some places happen where the gaps do weird things. At this place, the structure and the system are identical. Okay, really beautiful in math. All right, so I'm saying this is the picture of our 12 spheres out here, the outer parts of our simplest universe. It turns out that when we look at the Planck time, it has, in seconds, which is the base, the natural base of logic for it, has a power of 44, and space has a power of 35, charge has a power of 18, temperature has a power of 32, and mass has a power of 8. the same exact division parameters for this structure. Same exact division parameters. So we're just going to take hyperbolic rules that allow us to fit together all of these at the same time. We want to take this structure, so there must be some set of boundaries that allow us to compatibly be dividing one sphere 120 ways, another sphere 44 ways, another sphere 35, two more spheres 18, three more spheres 32, and four more spheres by 8. Okay. Another thing to note here, there's a ascension in power. This one's the controller of the system in the sense that there's more of it than anything else.
Okay.
Okay, 4 pi over 8, which is reduced to pi over 2. Same thing. Okay, but here we're writing them all in terms of how we're dividing spheres. This is the outside structure. We're going to pick 5 rules, 5 hyperbolic boundaries that connect this division structure. And with those hyperbolic rules, we'll then have exact definitions, meaning as many digits as you want. I can't give you an infinite number of digits, but I could give you 1,000,000, or I could give you 10 million, just not infinite, for what that actual boundary is, what that number is, which is a big advantage. Right now we have an actual sense for a boundary of time from the measurements. We have a sense for a boundary of space and charge and temperature and mass. We call them Planck time, Planck length, Planck charge, Planck temperature, and Planck mass, okay? But we don't know them very well because the way we know them is only from knowing the constants of nature, right? They're entirely got from the constants of nature. When we get the constants of nature, many of them have the similar dimensions. So you can take them and say, well, this is a constant of nature, it's got to be important. Here's a constant of nature, they have similar dimensions. Let me divide them out so they only end up with, say, one leftover dimension, right? That seems simpler somehow. Well, you can do that in many ways from many starting different constants of nature. And when you do it over and over and over, you end up pulling out the Planck time, the Planck length, the Planck charge, the Planck temperature, and the Planck mass over and over and over. But from the many different starting points, the number changes around the 7th significant digit every time. So there's like this vague, everybody agrees up to here, then everybody disagrees past that point, okay? And it really depends on which one you started with at that point. So there's like the sense that there's something being put together by these 5 things, but somewhere after 7 significant digits, there's something going on.
It becomes sort of subjective. And not...
Or there's something other factor involved.
Okay.
Yeah.
Yep.
Yeah. Okay. But here, we've now got a picture. Let me show you real quick on the screen here. I'm going to just give you 5 hyperbolic boundaries. We searched and searched and searched and found. So here's our minimal arena structure from the outside, our 12 spheres, okay? And here's the way we're going to connect the 8 and the 32 and the 18 and the 35 and the 44. They're all going to connect. This is the full set, and then we're going to, actually I need to say something about that. There's a rule to go from here to here. And I bet you that rule is the way they're connecting to begin with, since both of these are showing up. Okay, but this is just going to be how these division structures are all fit together at the same time, and you have to only use things that the hyperbolic figure 8 knot makes. Hyperbolic boundaries. Okay, cosines, hyperbolic sines, the Weierstrass constant, this is ijk, the units of square root of -1s. Okay, that's all we have there. That's it. Very simple structure. And we're claiming it's the structure that divides these things compatibly. And what does it do? It comes with a rotation that each division has in the balance. It's a way of dividing and rotating to fit. Okay? Each one has a hyperbolic, E is the base, so it's hyperbolic, rotation. This 0th rotation, ends up being the value, this number, for the digits of the Planck time. And the 44 is the power. And the same thing with each of these. They become modular representations of these boundaries fitting together, quite simple to understand, but more importantly, they're exact numbers. All these green digits here are digits we didn't have before. Okay, and we can get more. I just cut it off there because we don't have measurements to explain it beyond that precision. Okay, so these 5 rules now to explain why these 12 exterior spheres are dividing in unison. They can do it all at the same time without breaking the other rules for the other guy. That's what these boundaries do. Give us the 5 Planck constants to any precision we want. Now, we just need 2 rules. This one and this one. This is for how they're partitioning, how they hyperbolically partition all of those boundaries, and how they are fit together on the outside. That's it. Just 2 rules for the structure so that everything stays balanced. And with those 5 boundaries and these 2 rules, we have actually found, and note this comes from the structure of the hyperbolic figure 8 knot, right? The way it's partitioning. We found that the simplest possible system of persistence has these properties. This is a grid of 288 transforms allowed by those 5 boundaries, those 5 hyperbolic rules, the Planck constants, and the 2 rules for how they hyperbolically divide and how they're put back together. Okay, this 288 expressions nail all the constants of nature.
Are a result of the function
of these 2 rules. I'm going to go over the rules a little bit. This is just broken into the exterior part and the interior part. Okay, exterior, interior. The 12 spheres or the double covered interior sphere. Okay, the exterior part is made up of some boundary, but it has to be only expressions of Planck constants or things you can build from Planck constants. That's it. And the action, A here, is the action is just the geometric way you're fitting together those Planck constants. So if it's a 2 pi, then it means you're using a circle to fit together those Planck constants. Okay?
Okay.
So that's it. 2-part, outside, inside, exterior, interior, right? And we have an action on both, but the interior one only has one possible set of boundaries. It's always the same one because it's the same structure on the inside. It's not many options. Outside, we have 12 different possible ways, different structures of division. But on the inside, it's the exact same thing every time. So it's this. Planck length times the Planck mass over the Planck charge squared, and we take the magnitude of that because we're not taking the dimensions of it because it's the inside. The outside has the expressions of the dimensions. The inside is responsible for making the gap for that walled structure, right? Every gap has 2 sides, and it's the size of that gap on the inside that we're making here. So it's the size we care about. All right. This one is just a simple rule for how we're hyperbolically dividing, and the rule itself comes from the hyperbolic figure 8 knot. Okay, so let's do that now in more detail. It's a super short story if you're following. We have a description of a simple system you think you're seeing just right here. Of course, we want to actually model it in a 3D animation that's very, very beautiful, right? But it's just this many pieces to it. And the outside has this rule, right? And since it's dividing these many different ways, there must be 5 boundaries that fit together those ways, making them compatible. So we have 5 hyperbolic rules defining those boundaries, which match the Planck constants, according to our knowledge so far, and extend the claim for what those Planck constants are. But then when we use that, we can take this structure here for the hyperbolic figure 8 knot to find the rules that connect all of the actual measured constants of nature. Find the pattern in the constants of nature. This has never been done, right? In any other way, in any way at all, for a constant or a list of constants. This is all of them at the same time. Okay, I need to erase. Let's see.
So it's basically explaining the relationship between all of the constants of nature.
Yes, yes, yes. And if you know why they're holding and doing what they're doing, you can start using them on purpose. You do the right timing, do the right placement, do the right, you can start manipulating charge, temperature, mass, all of the ingredients just the right way to make the transforms that nature can already do. Instead of statistically trying to blow things up hard enough to make some certain thing happen. We can finesse it just right, save ourselves a lot of energy and get something fantastic. All right. The rule, if I take the dialogarithm, remember this was dividing the circle, the measuring golden ratio, it divided the circle in 6 pieces. 1, 2, 3, 4, 5, and this and this, right? So a third of a flip means you divide the whole circle into 6 pieces, right? So let's take the dialogarithm of the full cycle, 1. The difference between that and the dialogarithm of the half cycle, -1. Well, this ends up being equal to 4 pi over 8 squared. Okay, put it right here. 4 pi over 8 squared is the square root of our controlling equation here for our outside structure. We really like that number. And here it's directly in the same structural information as the hyperbolic figure 8 knot. In fact, it comes from two limits in its structure. Those limits suggest right away that we're making some Mobius connection. You know what I mean by that?
No.
A Mobius strip is like a strip of paper. You glued it back together or tape it together, but put a half twist in it.
Okay.
So that it only technically has one side now. Here we're talking about a system that's two-dimensionally splitting, but we're going to take one that goes half of a cycle and one that goes a full cycle. And a Mobius strip is exactly the thing that if you go around it one time, you've only gone halfway around in another way. You have to go around two times to be all the way, to be around once in the second way, right? So it's a two-part cycle in one way and a one-part cycle in another. And this, or a one-part and a half cycle, same thing. Okay, so a Mobius connection is directly implied here, which is a beautiful thing, but it also is characterizing the square root, right? Square this, it becomes to the fourth power. It's the same thing as our controller here.
Cool.
Okay, well, I want to start with our external way of dividing, and we're just going to pick a simple equation for hyperbola, because we need it to be hyperbolic, and that's it. 1 over x plus x cubed. If you set this equal to 0, you can check its roots, and they are equal to the imaginary golden ratio, 1 over the imaginary golden ratio squared, and 1 over the imaginary golden ratio squared. It has 4 roots. 4 roots. Okay? And all of them are just the imaginary golden ratio, but this one uses it twice and this one uses it twice. Okay, so you can tell that the structure, the hyperbolic structure we're picking here is married to the structure we started with, but this is our external way, or our way of thinking how we're hyperbolically cutting things up, okay? Hyperbolically dividing things up, or partitioning. So we call this the hyperbolic partition equation, but we're one step away here from what we really want. We want this hyperbolic structure, as it's hyperbolically tied together, it needs to turn itself inside out. Mm-hmm. Otherwise, it's just going to go to infinity, right? It's hyperbolic to infinity, and it's never going to close. So it needs to turn itself inside out. We need to change it or modify it by putting one closed loop in its structure. So as it goes out, it turns something around. And now it's inverted like a Mobius strip, and it has to do it again and again and again, over and over and over. Okay, but if we change this side of the equation, we need to change this side of the equation. I'll put a star over our 0. We need to complexify our 0, but we can't change it in any way that's not compatible with the structure we started with. So what are we going to do? Well, if we're sneaky, we can look at this structure and find out, asking Wolfram Alpha, what happens if I start with this? There's a 1 here and a 1 here in power. What if I put a 2 here instead? In there. Then what happens? And then what if I put 3s and 4s and 5s and 6 and keep going up? Well, you find out real quick that there's a 6 cycle. You get 6 different answers. Actually, it's 3 answers and then mirrored with a minus sign, the same 3 answers. And then it repeats over and over and over, no matter what number you put in there. You could put 12,000,007, okay, but it would still be one of those 6 answers. Okay, so there's a 6 cycle in here. If you put that one in here instead, you would have a 4 cycle. The point is, the 6 cycle has 2 zeros in it, right? There are 2 answers. You could put in 3s or 6s. So if I put in I times by dilogarithm of 1 over the imaginary golden ratio cubed minus the dilogarithm of the imaginary golden ratio cubed, now it equals 0. If I put 6 here and 6 here also, I would get 0. So there's 2 zeros in our cycle from this structure. All right, so since I'm going to complexify this 0, I need to do something to these zeros. There's another one. 0 equals, I'll just write it out, make it really obvious. Dilogarithm of 1 over the imaginary golden ratio to the 6th minus dilogarithm of the imaginary golden ratio to the 6th. So here's our 2 zeros. So this is what we're going to do. We're going to have to change our 0 because we've changed our system here. We made it invertible. We're going to just take the components that made our 0 to begin with and swap them. What happens when we swap them is it becomes this dilogarithmic difference I was talking about to begin with. This 1 cubed is -1, and 6th is 1. right? So it becomes this one right here, 4 pi over 8 squared. Okay, so what we need to do is we need to rotate our system to make our complexified 0. Let's move this over a little bit. 1 over x plus x cubed over 2 pi equals now e to the 4 pi over 8 squared minus some gap, some mass gap. Because we introduced a hyperbolic structure now that's got a separation in these surfaces. It's a non-zero, they're not touching, right? Some surface, some separation there. We call it the mass gap of hyperbolic structure. And the only thing that changes if you pick a different hyperbolic space is it has a different mass gap, right? You can model an infinite range of hyperbolic spaces that are scaled differently, but they're all hyperbolic spaces. They just differ by their size of the mass gap. So here now we've got our equation, our rule for how we're dividing things up according to the external reach of this guy, okay, hyperbolically. I should note for those who have been watching for a while, this can be written as I to the I to the negative pi over 2, which is how I usually write it. Okay, but today I'm writing it like this for us. Where am I going? Oh, so this is our one rule. Now we have this rule, and it has new roots. Our roots before were the imaginary golden ratio powers, right? Okay. And now the roots, those things themselves, got slightly morphed and changed because we twisted the system once, right? And we gave it a non-zero mass gap. By the way, I'm going to put in here, inspired from physics. There's one limit in mass in physics, and it's the biggest. Well, there's a limit at the bottom and a limit at the top. The biggest possible mass you can have in physics is the Planck mass. So we put in here the famous limit in physics called the Planck mass. Okay? And when we do that, we now solve for our equation and we get 4 solutions. What we call J1, J2, J3, and J4. All right, so these are our partition solutions for our hyperbolic structure. That's what they represent. They're geometric numbers like pi, like the golden ratio, but they specifically represent this arrangement in hyperbolic structure. Okay. That rule, now I just need one more rule.
So these are all symbols, representations that have already been, they're already used and discovered by...
The jeux, not at all. The jeux are entirely new.
That's something that you...
Everything else up until there is well known. Yes.
Interesting.
Yes. So the jeux are new numbers, and they have fantastic properties. We'll run through them. I'm trying to do it a little fast. I want to show you the second rule. This is just one rule now, and you can see where the rule comes from the structure we started with, right?
Okay.
It's just mirroring it on the outside. So we have to stay compatible with that structure, and it has the same root. Okay, good start. But now we need the rule for how we're fitting these things together out here. All right, so that rule is going to be some geometric action for putting together the boundaries on the external part. And then it's going to be fit together with an action on the internal and a fixed set of boundaries. It's the same inversion boundaries over and over. There's only, once you fix the gap size, then the cone is fixed. The size of the cone and everything and the way it relates to everybody else is fixed, right? So this is representing, that's why it has this symbol, the scale of where the cone or the inversion happens in the hyperbolic structure. Okay, that's what that one means. And it literally is just composed of the Planck length, the Planck mass, the Planck charge squared. Maybe take the magnitude of that. So the size of that tells you the size of our gap structure. Okay? And we're going to have some, for each different way we're fitting together these things together, we're making a different constant nature. Each way we fit these different partition structures together makes a different constant nature. And it has to match inside structure and outside structure. The 12 outside and the double covered inside. Okay. Well, that's pretty simple. We have fixed here. So there's only 3 things to check in this rule, right? And this, by the way, is going to give you constant of nature. The output here for every time we fit together things into this rule gives a constant of nature in the structured universe we're building, right? So this universe has so many constants of nature, 288, because it's tetrahedral, right? The miracle is that once we know that, we can take the constants of nature that actually exist, put them here, solve for the boundaries with the dimensions of the constant, solve for the primary action from the first bit of the number. You get the first 7-ish digits right. And then there's going to be, because this has a number that's basically 1 times 10 to the negative 7, real close to that. Okay, so it only comes into play at the 7th digit. That's why everything was going off there. And it happens to be made just from those 3 things primarily in our structure to begin with. All right, that's it. That's our rule for fitting things together. And this is our rule for how we break them apart. And they're both entirely simple structurally wise, right? I mean, I think you can see this one comes from the inspiration of the structure here. Nature picked a size. So said, well, let's just force the right size of mass in here to see what happens in our structure. Start learning the rules, and so we maybe find out why nature picked that size. Yeah. Mm-hmm. We're basically done. We've taken an understanding of the simplest universe that can be built, the simplest structure that you can form that then continues to perpetuate itself. And its division structure in that perpetuation is folding all of its boundaries and its parts inside out over and over and over along exact division specifications, right? Those very specific things happening, 288 of them. And we then took all the constants of nature, the 288 constants of nature, and started investigating to see if we could find a pattern using just these 2 rules and the 5 rules we have to specify more precisely the hyperbolic boundaries we're calling the Planck constants, okay? The ones fitting together all these external divisions at the same time. Great. So it's extremely simple, and it starts from the simplest geometry that can exist, as far as we know at this point in history, okay? It starts from the simplest structure that's possible logically, and its division structure apparently is entirely compatible and therefore perhaps responsible for the actual parameters of reality. There are repeatable features built into reality. Mm-hmm. And this is a story for a reality, a structured form that keeps itself, that partitions to those features. I'm extremely excited by this, as you can tell, because this doesn't mean we've now made a replicator. This gives us a framework by which it becomes possible to imagine how to build a replicator, right? What kind of geared structure, what kind of components, what kind of materials, what sort of ways are we trying to make these materials be manipulated inside the machine, and so on. This allows a whole slew of different ways of doing those things, using the actual constants of nature to do the transforms that they're already doing on the boundaries that they're working on, right? So we're not working on level of reality at that point right now because we've been missing the picture for what's going on that level of reality. But here I'm saying we have a picture for a description for what the simplest possible structured universe could be, or perpetual system, a system that actually has measurable properties in it. And that system has mapped incredibly well to all the measured properties we've wanted to explain. So now the goal is to look into these fantastic mysteries. This column, we have 8 times 36, 8 columns and 36 rows or equations per column, and that's 288. This one is composed of Planck constants in the boundaries. These are helping here. Too much helping here then. Okay. Planck constants in the boundaries, right? Every time here. 4 pi, 2 pi, J1 squared, or one of our hyperbolic partition parameters. The joule, the unit joule. There's a 1 there, okay? And the gig electron volt, there's a 1 there. All right. But on the right-hand side, it's just half of the real part of the I to 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 the I power tower. The infinite I to the I power tower, which you might not have any picture in your head what that is, right? Yeah. Here's our I to the I power tower. It spirals in, with each I you add, it gets closer and closer and closer and closer and closer to this point. And if you notice, There's actually a threefold symmetry here. There's a spiral going here, and there's a spiral going here, and a spiral going. There's three arms, and they're perfectly spaced. The cool thing about it is it was picked out by this entire swath of the constants of nature. Right? You see a big pattern here, right? These are all exactly the same. We have 28 of these down here, and they all have imaginary part of the power tower. And then we have 4 half imaginary parts and 4 half real parts. And then real quick, I'll add 6 more and 6 more real. So that's a total of 12 real plus 1, 2, 3, or half and half. That's 1 and half and half. So it's 14. 12 and 14. Wait, we had 12 spheres and 2 on the inside. Ooh, this picture's getting rich. Okay. And the imaginary power tower somehow has something to do with that? I want to look into this eye to the eye power tower a little bit. Just for fun. Eye to the eye to the eye to the eye. It's a fixed point of a fixed point equation. You can write an equation down for which it's the solution of it. Okay? And it's just this. X is extremely simple. Equals I to the x. Ooh, that's a short and beautiful equation, okay? But why is it true? Because if I put the answer here for x and here for x, well, since this is already infinite, I to the infinite i's is equal to I to the infinite i's. It's the same thing. Okay, so we can also rewrite this equation as, well, I've already written it up over here.
Now, I stands for?
I is the square root of -1.
Okay.
Yeah, the same I we started out with over there. You can also rewrite this equation. I have it over here. There we go. Fixed point equation for I to the I to the I is this, or you could rewrite it like this, or like this. And you will notice strikingly in that equation, there's a number, 4 pi over 8, which reduces, yes, to pi over 2. I'm leaving it in the 4 pi representation because of our sphere story, right? E to the 4 pi over 8. It's a hyperbolic rotation. In fact, it's half e. This is e to the 4 pi over 8 squared. Right? It's half of that guy. Beautiful, beautifully centrally right part of both parts of our picture there. The whole thing's coming down to just the binomial constructor rule and the hyperbolic partition equation, which are both understood as being the way we make sense of how the world gets put together once we form the hyperbolic figure 8 knot. Okay? And this partition set has been able to match within the measurement satisfaction, within the error bars that we're happy with, right? All the constants in nature, and that's how we found it. And we use them to search for the pattern that would be compatible with all this. And it's really, really, really symmetric. I mean, let me remind you real quick. We have 5 boundaries that divide 5 ways: 44, 35, 18, 32, and 8, right? Well, this whole structure is 2-part, if we remember. There's the left side, the outside, and there's the right side, the inside. It turns out there's exactly, if you count the number of constants, of geometric constants on the right-hand side, the unique ones, and list them all up, you get 44. If you count all the constants on the left side, you get 35. And magically, there's exactly 18 overlap between them. Oh, also, there's a lot of cool things going on with that. 288 is our division structure, our maximum tetrahedral division number. It happens to have 18 factors, meaning there's 18 different ways you can break up 288. 1, 288, 2, 144, and so I have a list over there, but 18 different ways. Or you can also get an 18 interesting from digit sum. 2 plus 8 plus 8 equals 18. There's a lot of symmetry happening in this structure. This is a language built into reality for the transforms that are allowed, for the structural components that can be in things that persist, atoms.
The building blocks.
So this is literally the blueprint of a language, the language of physics, right? And it all comes down to 5 Planck boundaries, 5 boundaries for the 5 different dimensions, under the projective balance, under the simplest possible projective balance or hyperbolic system.
So the hyperbolic figure 8 knot basically explains why all of these
Yeah,
exist.
yeah. These things are the reason all the things in physics are allowed. Anything that can happen in physics, simple things or weird things. So they're not just the structural equations for the structure of the world that they're framing. They're structural equations for the transforms that a world allows. It's mind-blowingly simple. So we just barely uncovered a pattern to the constants of nature, right? And it's a pattern that you can interpret in a simple way, meaning through the lens of the simplest structure of geometry. So that means now we got to use that understanding to start training our minds to think in this language.
Okay.
That's the first step, right?
Yes.
See what the elemental things.
How do we apply this?
Yeah, and then how do we apply it? How do we make it do these things? Now that we know that this is the structure, and that structure is already now in the stuff we're already looking at, right? It's not like this is a structure we could apply to something else. This is already applying to the structure of everything we've ever touched or seen. Some of these math concepts were relatively new to physicists, right?
Yeah.
I mean, projective geometry isn't something that's mainstreamly taught, even though physics is mainstream in bed with the Dirac equation, which came from projective geometry, but that's not the way we talk at this point.
Equation?
The Dirac equation, the foundation for all quantum mechanics.
Okay.
Yeah, quantum field theory. It characterizes the square root of that double shell. Yeah, so it's just characterizing the structure of hyperbolic space in a different way.
Okay.
And it gives you the rules, the basic rule set in quantum mechanics. But we had to put in the constants of nature to make it right. Okay, so the basic rule set has unitary operations. It's all acting on ones and ones and ones. And then you have to scale things by something to make it true. And we look in the real world and find what we have to scale it by, and it turns out these constants of nature, like Planck constant and the electron's mass and so on, are the things that scale its hyperbolic structure in order to give us the right rules for quantum field theory. Let's look at C. Remember E equals mc squared, your equation there? Well, here's the speed of light. It's the Planck length over the Planck time, which gives you the right dimensions for speed. That's cool. So this characterizes the boundary of speed, because we use the boundary of length and the boundary of time to form it. And the inside structure, maintaining the gap for that boundary, is the square root of the Giesecke constant, the smallest possible manifold. And this is the partition pieces. It's using J1 minus J2 for the partition to do it. So it's actually happening by having something on the inside fall apart. Okay? The thing's falling apart along the square root of the boundary of the smallest thing that if you fall apart on, you're still being balanced. The smallest thing. The fastest velocity is having that exact perfect relationship. I love it. Just understand how to do the transforms between mass and energy. I mean, we have one insight now. There's this tower of eye to the eye involved in all the transforms. So we got to figure out how do you make one step up. Because it looks from the eye to the eye to the eye to the eye tower symmetry, when you figure out how to make one step along that tower, every other step is exactly symmetric. You can just do it again. Right? Beautiful insight. When you figured out the machine that steps between the eye to the eye to the eye towers in your structure, you've figured out how to connect and transform between 36 of the 288 constants of nature, how to use them, just from that one insight. Because we now have this pattern that tells us they all connect like that. So it's a huge step we're at, and we're just starting now to see what to do with it like that. But that's the story. We have a story now that does connect all the constants of nature to a simple geometry, the simplest, by definition, geometry that can be persistent, and its partition structure. That's it. We can now visualize a universe that contains this partition structure and has all those features or qualities that we call constants of nature. So this is the alphabet
Figuring out how
of invertible transforms, or this is the allowed operations on things that persist. So if you want to be made of atoms before and after, then this is the way. This is the rules for all the steps, all the paths between.
So now it's just putting the alphabet together to make how they
So there's a lot we can do now. It looks like the entire structure of physics can be completely whittled down or fit into partition theory. Fantastic.